Right now, the Wi-Fi router in your home is making decisions thousands of times every second. In each millisecond, it receives data, reads network addresses, checks whether the air is busy, decides which device should be served first, and coordinates several antennas at once. If those decisions were only slightly slower, videos would freeze, calls would break, and games would lag. Yet most people still think a router is simply a box that broadcasts Wi-Fi. In reality, it behaves more like a real-time traffic control center. The process begins the instant you press play on your phone. A tiny network request is created and sent toward the router. The device itself appears motionless, but beneath the enclosure its processor, memory, and timing circuits are already synchronized. As the packet reaches the mainboard, the processor examines its destination, checks that the information has not been corrupted, and searches its routing table for the correct path. This happens in microseconds, before the first frame of the video has appeared. A router does not create the internet, and it does not store the internet. Its job is to move packets between networks. Each packet contains addressing and control information that tells the router where it came from and where it needs to go. The processor compares those addresses with internal forwarding rules, selects the correct interface, and sends the packet toward the next stage. Millions of similar decisions happen continuously, while other packets arrive from phones, computers, televisions, cameras, and smart devices throughout the home. The packet still cannot be transmitted immediately. It first enters a queue, where the scheduler decides exactly when it should move. Some packets are urgent, others can wait. A live call or online game is far more sensitive to delay than a background download. Quality of service allows the router to recognize these differences and move time-critical traffic ahead of less urgent data. The goal is not simply to make everything faster. It is to use limited network resources where delay would be noticed most. Once permission is granted, the packet enters the radio frequency front end. Here, digital information is converted into a signal that can travel through the air. Filters remove unwanted frequencies, mixers place the data onto the correct carrier, and amplifiers raise the signal to the required level. These components work with extremely precise timing, because even small errors can reduce signal quality before the transmission reaches the antennas. But before the router transmits, it listens. Wi-Fi devices share the same radio environment, so two devices transmitting at the same time may interfere with one another. The router checks whether the channel is busy. If another nearby device is already using it, the packet waits for a short interval. This behavior, known as collision avoidance, is far more efficient than sending immediately and then repeating the entire transmission after the data is lost. When the channel becomes clear, radio energy flows into the antenna array. Several antenna elements can operate together, adjusting their timing and phase by tiny amounts. Instead of sending energy equally in every direction, the router can shape the outgoing wave so that more of it reaches the intended device. This technique, called beamforming, strengthens the useful signal without simply increasing transmission power. The wave then moves through the room. It may travel directly toward the phone, but much of it also reflects from walls, ceilings, furniture, glass, and other surfaces. These reflected paths arrive at slightly different times. In older systems, multipath could create serious problems. Modern receivers compare timing, phase, and signal strength, then combine the useful parts of several paths to rebuild the original data more reliably. Inside the smartphone, the incoming radio signal is amplified, filtered, and converted back into digital information. The packet is reconstructed and checked. If it arrives correctly, the phone immediately creates a small acknowledgement packet and sends it back toward the router. That acknowledgement tells the router the transmission succeeded. The completed packet can then be removed from memory, resources are released, and the next waiting packet moves forward. While one packet completes this cycle, hundreds of others are already moving through the same hardware. Their destinations, priorities, and deadlines are different. Some leave immediately, while others remain in memory. The queue is never fixed. It expands, contracts, and reorganizes continuously as new traffic arrives and completed packets disappear. The router is not handling one simple stream. It is coordinating many independent conversations at the same time. Modern Wi-Fi improves this process with OFDMA. Instead of giving the entire radio channel to one device for each transmission, the router divides the channel into smaller resource units. Different devices can receive their own sections during the same time interval. A phone downloading video may use one group of resources, while a laptop loads a web page and a smart speaker receives a small control message. The channel is shared more efficiently, especially when many devices are active. MU-MIMO adds another layer. With multiple antennas, the router can create several spatial streams and communicate with multiple compatible devices at once. The signals travel through the same room, yet their timing and spatial characteristics allow the receivers to separate them. What appears to be one invisible wireless field may actually contain several independent data streams, each carrying different packets toward a different device. The router keeps measuring what happens after every transmission. It monitors signal quality, failed packets, changing interference, and overall network load. When conditions become worse, it may use a more robust modulation method that carries less data in each symbol, but is easier to recover. When conditions improve, it can increase efficiency again. The fastest setting is not always the best one. The router is constantly balancing speed against the probability of successful delivery, and the journey did not begin inside the home. Before a video packet reaches the router, it may have traveled from a distant data center through the internet backbone. Large carrier routers examine enormous routing tables and choose the next high-capacity link. Electrical data is converted into pulses of laser light and launched into optical fiber, where it can travel across cities, countries, and oceans with little loss. At the service provider, an optical line terminal schedules data for thousands of subscribers. The downstream optical signal passes through passive splitters, sending different branches toward different homes. Inside the home, the optical network terminal receives the light, converts it back into electrical data, and places the packet inside an Ethernet frame. That frame travels through the cable to the router's WAN interface, where the local processing cycle begins again. The router now recognizes a new packet arrival. Memory reorganizes, the scheduler evaluates priority, the RF hardware prepares another carrier, and the antennas coordinate another transmission. At the smartphone, the receiver combines direct and reflected paths, rebuilds the packet, and sends another acknowledgement. The same sequence repeats continuously, not only for video, but for calls, games, messages, cloud backups, websites, and every other online activity. This is why a router is better understood as a real-time decision engine. It must choose a route, manage a queue, protect urgent traffic, wait for a clear channel, shape a radio signal, coordinate antennas, confirm delivery, and immediately begin again. The environment never stops changing. Devices move, doors open, people cross the room, neighboring networks become active, and the router continually adjusts. So the next time a video begins instantly, remember what happened before the first frame appeared. A request became a packet. That packet crossed backbone routers and optical fiber, entered your home through an optical terminal, passed into the router, waited for its turn, became a radio wave, crossed the room, and was reconstructed inside your phone. An acknowledgement then returned, confirming success and making room for the next packet. The router still appears silent. Yet inside, thousands of packets are entering, waiting, routing, transmitting, returning, and completing their journeys every second. Behind those blinking lights is a machine coordinating semiconductor logic, networking protocols, optical communication, and radio physics in real time. It is one of the most sophisticated systems found in an ordinary home, quietly keeping the modern world connected one packet at a time.